So hello, my name is Yumi and thank you for coming to my presentation. My research is about creating creating sustainable structural coloration by synthesizing starch acetate nanoparticles in order to replace toxic textile dyes. But first, I would like to thank Papa Jack for giving me the opportunity to continue to do research under his Kay Fellowship. So the purpose of this research is to replace textile dyes using a sustainable method, since dyes have harmful impacts on public health and on the environment. The wastewater that is produced after the dyeing process is drained back into bodies of water near textile factories, causing allergic reactions and disturbing cell functions to people working and living near the factories. The wastewater contains toxic chemicals and heavy metals that decrease soil productivity, and it takes away freshwater sources for millions of people. An alternative to these harmful dyes is the implementation of structural coloration onto textiles. But how does structural coloration exactly work? So in the case of a regular object like an apple, we see the color red because when light hits the apple, wavelengths in the visible spectrum of red are reflected off of its molecules and into our eyes, while all other wavelengths are absorbed. Structural coloration uses the same mechanics of reflection and absorption of light when we see a chemical dye, but unlike dyes, it depends solely on the structure of the object. So a prime example of structural coloration is the morpho butterfly, which has nanostructures on its wings that reflect light in the blue range of the visible spectrum, creating their blue iridescent color. So the colors of structural coloration changes as the diameter of the structure decreases or increases, and it reflects smaller or longer wavelengths respectively. And the nanostructures created in this research are nanospheres. And something to avoid in my structural coloration is iridescence, so that the color does not change due to viewing angle. This can be achieved with monodispersed and short-range order of particles, which is when the particles are uniform in size and they form small ordered regions that don't link together at longer distances. This combination makes the light scatter in every direction equally, and therefore there's no optimal angle to view it from. So in my previous research last year, I successfully spray-coated non-iridescent structural colors ranging from red-violet, violet, blue, turquoise, green, and yellow-green by synthesizing polymethylmethacrylate nanospheres, or PMMA nanospheres. However, PMMA is a nanoplastic, and nanoplastics are harmful to the environment, so it is not sustainable for large-scale use. It's important to note that PMMA was used as a proof of concept. We chose to synthesize PMMA since it was a reliable method and had the most potential for success. The ultimate goal of this research is to create sustainable nanospheres, and one such sustainable alternatives are starch acetate nanospheres, or SANs, which are biodegradable. SANs are also the best alternative since they can be monodispersed and in the size range that will reflect light in the visible spectrum. And also there has been few research that has created SANs for the purpose of structural coloration, or no research. So this is more of an entirely new research. So the research on synthesizing SANs has two parts. Part one consists of creating starch acetate, and part two consists of making the starch acetate into nanospheres. So part one is to create the base of starch acetate. To introduce starch acetate a bit more, it is often used in the food, cosmetic, and pharmaceutical industries as a great stabilizer, thickener, binder, and food additive. The reaction to create starch acetate consists of stirring dried cornstarch, acetic anhydride, and aqueous sodium hydroxide for an hour at around 110 degrees Celsius. And before the reaction, the starch is dried in order to reduce the chances of its water molecules interfering with the reaction. The maximum degree of substitution of 3 is our goal because it will give us the most stable and monodispersed nanospheres. To explain what that actually means, the starch's hydroxyl groups are substituted by the acetyl groups from the acetic anhydride, giving the starch acetate functions. And there are 3 free hydroxyl groups on each starch molecule available, so the maximum degree of substitution is 3. And it's our goal to reach a degree of substitution of 3, since starch acids of lower degrees of substitutions are used more for food additives and stabilizers, while higher degrees of substitution increases the starch's hydrophobicity and thermoplasticity, which is the capability of it to soften or fuse when heated and then harden when cooled. Starch astates of higher degrees of substitution are used in biodegradable packaging or as adhesives and are just more suitable to make nanospheres out of. So the final product after the reaction is milky white with a paste-like texture. To get rid of the remaining acid in the product, the Buchner funnel system filtration is used, and then the starch acid is dried in the oven at 90 degrees or 80 degrees Celsius overnight. Once dried, it is grinded into a powder using a mortar and pestle. This process is repeated twice to ensure that only the starch acetate remains. The degree of substitution is determined with a back titration. A back titration is a method where the concentration of our starch acetate is determined by reacting with a known amount of excess reagent, which in our case is sodium hydroxide, that is hydrolyzing the substituted groups in the starch acetate. And then the remaining excess sodium hydroxide is then titrated with another second reagent, which is our hydrochloric acid. The second titration's result shows how much of the sodium hydroxide was used in the first titration, and that allows us the starch acetate concentration to be calculated. And then the volumes and molarities of the solutions used are plugged into this long equation to find the degree of substitution. So here's a table that summarizes the various ratios I used in my starch acetate syntheses, as well as the average degree of substitution for each. The first ratio used originated from Mark and Maltretter, the top one, with an average, or the second one, with the average of 1.6, and then the next ratio is Zhu et al. With the average of 0.49. The highest degree of substitution achieved was by reacetylating store-bought starch acetate with an average, or highest average, of 2.45. Its original degree of substitution before being reacetylated is 0.53. And lastly, the degree of substitution was measured for pure cornstarch, which was 0.0007, which is close to our theoretical zero, showing that our measurements and method of determining degree of substitution were reliable. So the second step after creating starch acetate is to make nanospheres out of them. Usually, sands are used for controlled drug delivery and have never been created for the purpose of structural coloration. However, here we will be synthesizing sands using the starch acetate we made in hopes of creating structural coloration. Within this step, the second step, are two more steps, and the first is to create nanospheres according to the Oswald ripening theory, where droplets of particles collide in order to form larger ones so that they can reach a more stable state in which surface area is minimized. And basically, a solution of our starch acetate in acetone is dropped into a solution of distilled water in acetone. And the second step is to aggregate these nanospheres into larger nanospheres inside a hydrothermal autoclave container so that they're in the size range to reflect light in the visible spectrum. The hydrothermal autoclave allows them to aggregate inside water at higher temperatures and pressures than usual, which quickens the process. The size of nanospheres can change based on the temperature and the time it is in the oven. Although we were able to attempt these processes, we were not able to create structural coloration as there were many limitations to this research, some expected and some unexpected. Some of the limitations are that we cannot see the nanospheres without an electron scanning microscope seen in the first picture, and thus we don't really know if our particles are monodispersed or in the right size range, and we're currently contacting Manoa for one. Other potential problems include the fact that the acetic anhydride used was old and perhaps not the best to make starch acetate out of, as well as the sodium hydroxide being difficult to use because it absorbs moisture from the atmosphere, so its weight is often inaccurate. And lastly, there's little research done on synthesizing sands and none for the purpose of creating structural coloration, making it difficult to do in a high school lab. An alternative, or on the side, we briefly tried chitosan nanoparticles because the two main ingredients are chitosan and sodium tripolyphosphate, or TPP, which are both biodegradable. The reaction to create the reaction between the chitosan and TPP is called ionic cross-linking, where a charged polymer cross-links with an ion of the opposite charge to create a bigger particle. They were not particles. We centrifuged them and looked at them under a compound microscope, and were not nanoparticles. And some problems include that extremely small amounts of chitosan were used for each reaction, ranging from 0.5 to 1.5 milligrams per milliliter, making it difficult to manage. So in conclusion, the main results from this research was successfully synthesizing starch acetate and also synthesizing starch acetate with a high degree of substitution of 2.45. And this is an important and necessary step for future research. Some advice I have for future Kay Fellows is to be interested in your topic, as it will motivate you throughout the at times grueling process. And you should also anticipate obstacles and don't give up when you meet them. Finally, I would like to give acknowledgements to the people who made this research possible. Thank you to my mentor, Ms. Sailors, for coming in every day and giving me endless support and knowledge. I couldn't have done it without you. I would like to thank Dr. Chan for her advice and help when we needed absolutely anything. Thank you so much. Here are my references, and thank you for listening.